Okay, we're back in person. Again, my apologies for missing or not being live for the past couple of lectures. I had a couple travel engagements that just happened all at the same time. And my hope is that I don't really have to miss any more class for the semester because I don't like doing that. I was asking everybody in class just a question on logistics. I asked a couple people before class started, but I'm going to ask everybody here. Do you all prefer the Premiere, or would you just prefer I just post them?
I'm pretty first.
Because we got some split answers. Some people said Premiere, where the video shows up live like Monday at 11 or Friday at 11.
I'd rather you just post. You have more time to look at.
Okay,
Yeah.
all right.
Availability. I feel like that.
Okay, that's fine. I was just curious. I mean, I sort of did that because I don't know, I figured that it would just show up whenever we would have class, but it's a fair point. Maybe I should just post, like if I'm gonna miss a couple classes, just post the darn thing. Okay, so just a little bit on logistics. Attendance grades are up to date. I counted everybody present for the 2 days that we missed, so everybody was present those days. Homework 2.3 is due today, and homework 2.2, I believe, is graded. And all the solutions and whatnot up to 2.2 are posted. So they should, in fact, if you check now, the solution to 2.2 should be live. Today is, okay, so to explain what we're doing today, we're not really doing anything that is appreciably new today. What we're doing today is putting it all together, okay? So what we've been doing for the past few lectures is learning about each of the Lego blocks. And today, we're going to put it together, okay? So today is going to begin our discussion on the analysis of tension members, okay? We're going to have 2 lectures on the analysis of tension members. And what I mean by the analysis of tension members is, given a tension member, does that member satisfy all pertinent limit states, okay? And the reason that we do this first is because once you understand that process, you can then ask, given a set of criteria, what tension member should I use to safely and adequately resist those loads? And that, ladies and gentlemen, is tension member design. That is steel design. So we do the analysis first, and then we get into the steel design. Okay, so let me pull up the lecture real quick and go through a few things. And so a lot of what I'm going to say is just sort of regurgitating initially stuff that we've already looked at, okay? So the first thing to point out is just our general concept of LRFD. We've been talking about it. Today we're going to employ it, okay? We're actually going to use LRFD limit states today. So remember, we deal in factored loads and factored resistances, right? So we take a nominal resistance and adjust it by some resistance factor to achieve a usable resistance, or a factored resistance, BRN. Today we're going to be doing PNs because it's all axial loads. On the load side, we do not deal with just dead loads and live loads. We deal with factored load combinations, like 1.4 dead, 1.2 dead plus 6, or 1.2 dead plus 1.6 times the live. And then we use the worst case scenario. As long as the factored resistances are greater than or equal to the factored loads, we know that our structure is safe. Speaking of those load combinations, these are the load combinations that we use in LRFD. Today, we're really only going to need to use the first 2. And I would argue that for the vast majority of problems that we deal with in this class, really the first 2 load combinations are going to be what we end up using. And that's for a couple of reasons. The first is really just to sort of make it easy. Like once you understand how to, factor your loads, adding more load combinations just creates more busy work. But 2, pretty much every structural element that you design is going to have to withstand some degree of dead load and some degree of live load. Like to make the point, not every structural element has to withstand snow loads, right? Really only the ones on the roof, right? Not every structural element withstands wind and earthquake loads, right? Only some of them do. But everything withstands dead and live. That's kind of why we use that one quite a bit in class. So here are the 2 limit states for tension members that we've looked at so far. We are going to add a third one here in about a week or so on block shear, but we'll get to that one here in a bit. That equation is a little hairier, but the process is pretty simple. So for example, for gross section yielding, the nominal resistance is Fy times Ag. The resistance factor is 0.9. So the factored resistance according to gross section yielding is 0.9 Fy Ag. Fy being the yield stress and Ag being the gross area. Now for net section fracture, we need a couple different pieces of information. We need Fu, but we also need the effective net area. And the effective net area is the net area times the shear lag factor. So you can start to see probably what I meant by saying that we've been talking about all the Lego pieces and now we're putting them together. I mean, we had 2 lectures just devoted to that term, and we had a lecture devoted just to that term. Now that you understand each of those pieces, putting them together hopefully doesn't seem so scary, that it all seems pretty digestible. If we want to look up the steel data, or the yield stress and the tensile stress, we can look at that in either table 2.4 or 2.5. Table 2.4 is if you're looking at rolled shapes. Table 2.5 is if you're looking at plates. This is definitely a section of the manual that I would put a bookmark in, because we'll be looking at this table quite a bit throughout the semester. Now that being said, I think there are a couple of steel grades that to be clear, I do not think you should memorize things in a class like this. But that being said, there are a couple steel grades we're going to see a lot of. For example, A36. Yield stress is 36 KSI. Ultimate tensile stress is 58 KSI. I'm not saying you need to memorize that, but you probably are going to, just based on how the class works. The 3 most common grades that we'll end up using this class are probably A36, A992, and A572 grade 50. And A572 grade 50 and A992 are pretty much the same from a material property standpoint. Okay. Now, our complete expression for net area, so now we're able to speak the same language now. So our complete expression is to take the gross area, subtract any area lost due to the presence of bolt holes, but then add any necessary stagger factors. Okay? So in order to subtract the area lost due to the presence of bolts, we take the diameter of the hole times the thickness, but I should say we take the effective hole diameter, which is the bolt diameter plus 1/8 of an inch. Remember, we add 2/16, 1/16 for erection tolerance and 1/16 for the damaged material around the hole. And then we add stagger factors. S is our longitudinal spacing, G is our transverse spacing for any diagonal bolt paths. And that's for bolted connections. For most welded connections, the net area and the gross area are the same thing, because you're not removing any material from the connection. Any questions on net area or stagger factors or anything like that? All right. And then finally, shear lag factors. Well, from the limit state perspective, this is another table that I would bookmark in your manual, because we're going to use this one a lot. This is where we compute the shear lag factors that we use to adjust our net area. To be clear, there's a strong possibility that multiple cases may apply to a given connection. Okay. For example, the one that we do today is going to have 2 cases. It's going to have case 2. It's going to have case 7. So make sure that you're going through that. What I want to do is put all that together and do a full-blown start-to-finish problem. So that's what we're going to do. We're going to look at this member. Let me pull this up in the notebook so that you all can copy this down as I'm talking about it. Okay. All right. So what we're going to do is start to finish look at the following problem. I have a 40-foot long tension member. It's W8 by 24. It's made out of A992 steel. It is to be used as a tension member. I've got the connection scenario right here, right? We're going to put some load on this tension member. We're going to put a dead load of 80 kips and a live load of 90 kips. I'm going to throw out some terminology out at you right now. I have here on that first bullet, I say, can the member safely resist these service loads? So service loads of 80 kips of dead and 90 kips of live. That term service load is a fancy way of saying those loads are not factored. Okay? So if you ever hear you use the term service load, that means unfactored. So to put it in perspective, if I wanted to factor those loads, I would need to add do the 1.4 dead or 1.2 dead plus 1.6 live. Some problems in this class, you are going to be given the loads and they are already factored. So that's where the terminology of service loads versus factored loads is something that you need to pay attention to. So we're going to get, given this tension member, we are going to ask whether or not this tension member can safely resist the loads that it's subjected to, but we're also going to ask whether or not this tension member can meet recommended slenderness limitations. And what are those recommended slenderness limitations? L over R what? Has to be less than 300. L over R being less than 300, to be clear, is a limit that is applied only to tension members. And what I mean by that is, if we're looking at members in compression, no compression member is going to have an L over R of 300. If it had an L over R of 300, that thing probably going to buckle like crazy. So we have an effective slenderness that we use for columns, and we usually deal with slenderness values that are much less than 300. We're usually dealing with like 80s or 90s or things like that. But columns like to buckle, so slenderness is a little more important for columns than it is for tension members from a strength limit standpoint. All right, everybody good? Okay. Now, the first thing in any steel tension or in any steel design problem, primarily cases like this, is the first thing that you kind of got to do is start looking up stuff. Steel design is a very reference-heavy science, okay? So what we're going to do is we're going to take this problem statement and let's start digesting what we can glean from the problem statement. And the first thing that I want to look at is this highlighted portion right here, okay? We know that this tension member is made of A992 steel. So if I have a tension member of A992 steel, what does that tell me? What can I find?
Yielded tensile stress.
The Fy and the Fu. What is Fy for A992 steel?
50.
And what is Fu?
65.
All right, and you found that in table 2-4. So notice how I'm placing references, excuse me, for every data point that I look up from the manual, okay? And I'm going to try and be diligent on that as we do problems in this class so that you understand where I'm getting stuff, that I'm not just making this stuff up, okay? Now, let's look at 3/4 inch diameter bolts next. So, looking at the bolts, we have a bolt diameter of 3/4 of an inch. What does that tell you? If I know the bolt diameter is 3/4 of an inch, where do I go to next? Add an eighth to get what?
7%.
More than that, but
Your
the hole diameter, the effective hole diameter. Okay. Now, we're going to get to that 40-foot long here in a second because I think everybody can agree that's probably going to affect the slenderness. But now let's start looking at this W8/24. Okay? All right. Now, so I'm going to need your help on this one. Okay? Now, one of the things that you find with steel design is that, you know, right now, okay, so let me ask you this way. everybody that brought your AISA 15th edition sealed construction manual, open it up to table 1-1 for the properties associated with the W8/24. Now I want to have a discussion right now, because I want you to be engineers about this instead of me just telling you what to do. Now here's the problem. The problem's right here on the screen. Okay, has everybody got to the W8/24? So can somebody yell out a property that for this problem they think we're going to need for that W8/24? Like what property do you think we're going to need? Give me one of them.
Area.
The area. We're going to need the gross area. That's right. What is the gross area for a W8/24?
7.08
7.08. 7.08 what?
inches squared.
There you go. We're going to need that property, obviously. We're going to need that to do net area and gross area. We're going to need that. Okay? Look at the tension member. Anything else you think we're going to need? What other property do you think we're going to need to be able to do this problem?
Thickness.
Thickness of what?
Flange.
The flange, because the bolts are going through the flange. That's 100% right. What is the flange thickness?
0.400.
That's right too. Okay. Now, I'll tell you right now that will get us most of the way. Okay? We're going to need more properties though. Okay? I'm going to probe you for one set of properties, and the other set I'm just going to say, trust me, we're going to need them. We're going to be assessing strength limit states, gross section yielding, net section fracture, but we're also going to be addressing slenderness limitations. If I say we're going to be addressing slenderness limitations, what does that tell you that we need for this W8/24?
All the R values.
The R values. We need the radii of gyration. Okay. Now for W sections, there's just an RX and an RY. For angles, there might be an RZ. But for symmetric cross sections like this, there's just an RX and an RY. What is RX for this W shape?
3.42.
Okay, what about RY?
1.61.
Okay. So those we know we need. Now there's a couple other properties that right now don't seem very obvious. Trust me, we will use them, okay? Just trust me. Okay, and those two properties are the flange width and the depth. We are going to need those properties. Okay, what is the flange width? Why did I put two equal marks there?
.5.
6.5 inches. And the depth.
7.93.
7.93. Okay. Now, it is not overtly obvious why we need those two dimensions. It will be later. So just trust me on that, okay? I would expect doing this homework problem, like if I just gave you this as a homework problem, you probably wouldn't look those up. But then later on in the problem, you go, oh, dang it, I need those. So trust me, you'll see why. Okay. Now, we have the following limit states that we are going to assess. So gross section yielding and net section fracture. Now, in order to compute the capacity for gross section yielding, how do we do that? What's the expression? Anybody remember? I'll start you out. It's 0.9 something for gross section yielding. There you go. Okay, what about net section fracture? I'm just writing it here on the board just so that we have it here for reference. We're going to put it here on the screen here in a second.
0.75 FU.
Okay, so here's our expression. So let's take a look at these expressions. So let's start off with gross section yielding. Do we know that quantity? Do we know Fy?
Yep.
Do we know Ag?
Yep.
Let's compute it. Let's do it right now. So gross section yielding. So what this is saying is how much usable capacity do we have in that gross section before the main body of the member starts to yield. And we compute that as phi PN, so phi sub T for tension members, is 0.9 Fy Ag. I'm going to redo that. All right, so what do we get for VPN? Forgot my subscript. Dang it, not only did we have to bring our manual, but we had to bring our Casio FX115ES Plus or similar scientific calculator. Goodness, right?
318.6.
318.6, so I have a second?
Yeah.
Okay. $318.6 what? Kips. Okay, so what I'm going to do is I'm going to put a box around that and say gross section yield. Okay. So there's one limit state capacity figured out. Okay, let's go to the next one. All right. So what about this one? Okay. We know the 0.75. We know the FU. Do we know the net area on this shape yet? No. Do we know the shear lag factor? No. So now we need to handle those one at a time. So now let's talk about the net area. Okay. Let's see if we've learned anything over the past couple lectures and see if we can sort of diagnose what we need to do here. Do we have any stagger to worry about on this problem? No, we don't have any stagger factors to worry about. So our net area is just going to be the gross area minus the area lost due to the presence of bolt holes. How many bolts are we going to subtract from the gross section in order to get the net area? 4, because if we samurai sword or lightsaber through this section, we're only going to cross through 4 bolts, okay? And so we're taking the diameter of the hole times the thickness of what? The flange, exactly, yeah, because the bolts are going through the flange, right? So the gross area minus 4 bolts, the diameter of the hole times the thickness. So our net area is going to be the gross area minus 4 DE TA, right? Pretty simple because we've done problems like this before. So we got our gross area minus 4 times 7/8 of an inch. We figured that out already. 0.4 inches. And so our net area is what? I am not very coordinated. 5.68. Do I have a second on that?
Yep.
Okay. Good deal. Okay. So that's so let's go back here. So we've got that figured out, that figured out, that figured out. Now the shear lag factor, right? So the shear lag factor means we got to open up table D3.1. So we go out here, let's go to my AISC files. I'll pull up the spec here. Because you all, I posted this on Blackboard, so everybody has this. Let's go to chapter D. Ooh, go ahead. I'm pretty close. So we're on 16.1-30. Woo! Okay. So remember what we do is we start at the very top and we just go case by case and see how many cases apply to our situation. So does case 1 apply to our problem? You're shaking your head no. Why? Let's remember what case 1 is. Case 1 says all tension members where the load is transmitted directly to each of the cross-sectional elements by fasteners or welds. Is that the case on this problem? And you're shaking your head no. Why?
It's not the web.
There's no bolts through the web. Exactly, right? Only the flanges are connected with fasteners, not the web. So case 1 is out, right? So remember, really the main difference between case 1 and case 2 is case 1 is all of the elements are connected. Case 2 is some of the elements are connected. So are we going to have to consider case 2? You bet. We're definitely going to have to consider case 2. Okay? What about case 3? Do we have to consider case 3? All the tension members where the tension load is transmitted only by transverse welds to some. Nope, not going to have to worry about that. No welds on this problem. What about case 4? Plates, angles, channels with welds. No, got to worry about that. Case 5, round HSS. HSS stands for hollow structural sections. So if you ever see hollow structural sections, we're talking about square tubes or we're talking about pipes, right? So for those of you in capstone, we might be using some HSS sections for the canopy. You see HSS in a lot of industrial applications and places like Walmart. The columns at Walmart are HSS sections. So we were talking about Walmart and capstone earlier. So. Okay. Rectangular HSS for section 6, ain't got to worry about that. What about case 7? Case 7, WMS or HP shapes. Are we dealing with a W shape on this problem?
Yes.
You bet. So we definitely are going to be worrying about U7. And for U8, U8 is single and double angles. We don't need to worry about that. So let's go to our shear lag factors, and we need to consider case 2 and case 7. So okay. Actually, let me do this. Put a reference on that. On that sucker. Okay. So case 2 and case 7. Now, case 2 is going to be a little interesting. All right. I think I mentioned this in the shear lag lecture, but we didn't have any examples on it because I said this is coming later. Well, it's later. This problem looks like this. Okay? We have a W section connected via the flanges, right? Do you remember me talking about this in that lecture when you have a W section connected via the flanges? Do you remember what we do? We talked about it, but we didn't do it. Let me pull up those notes, because I know I mentioned it. All right, so let's talk about case 2. Let's go back to case 2. So this is our expression for case 2, right? It's 1 minus x bar over L. But I name them differently because I want to make sure we understand what the x bar and what the L is, right? Now the L is the length of the connection, right? Do you remember how you find the length of the connection?
Outside bolt, outside bolt.
Outside bolt to outside bolt. However that distance is, that's L sub CON. Well, what about x bar? X bar is the distance from the connected face to the centroid, right? So if we have a channel, we go from the connected face to the centroid, and for channels, it happens to be X bar. If we're talking about angles, if it's the long leg, it's X bar. If it's the short leg, it's Y bar. Y'all remember this? And then I kind of threw this up here. I said there's a special case for X bar. And the special case for X bar says that if you have a case like this, a W section connected via the flanges, in order to get the X bar for shear lag, we have to convert it to an equivalent WT. The idea is that if you have a W section connected via the flanges, and you connect it here and you connect it here and you yank on it, the idea is that half the load goes to the top of the section, half the load goes to the bottom of the section. So to get the connection eccentricity, we look up Y bar for this equivalent WT. Y'all remember me mentioning that? I know I mentioned it. It's like I know I did because it's right there. So what we're going to do here is this, okay? So the section that we're dealing with, on this problem is a W8 by 24, okay? So what we need to do is convert that to an equivalent WT. And we need to look up the Y bar for that, okay? So X bar sub CON is the Y bar for the WT. Now, if this is a W8 by 24, what's the WT shape that we look up? Well, let's keep in mind. W8 by 24, what does the 8 mean? What's that? What's the 8? If I say I have a W8 by 24, what does the 8 mean?
It's 8 inch whatever, right?
About how deep it is, right? So if this is about 8 inches deep, how deep is this? 4 inches deep. So we need a WT 4. And what's the 24 mean over here? How heavy it is, right? Pounds per foot. So if this is 24 pounds per foot, how heavy is that? 12 pounds per foot. So, somebody tell me for a WT 4 by 12, what is Y bar?
0.695.
0.695 inches. So therefore, X bar sub CON is Y bar for a WT, man, my handwriting's horrible. WT 4 by 12, which is 0.695 inches. Better up here too. That is a common case that you find among tension members. Again, as I told you when I first started introducing shear lag factors, you're starting to get to an area of civil engineering and engineering in general where you're starting to deal with empirical expressions. Expressions that don't quite perfectly have some direct connection to some mechanistic rule of physics or anything like that. It's folks going down to the lab, yanking on a bunch of tension members and finding a simple model that fits the data as best as possible. And we use those empirical expressions all the time in all different aspects of engineering. The actual proposed shear lag factors that came from the research on this were actually much more complicated, and then the folks that wrote the specs said, let's keep it simple. So while it's a little weird, it's not hard, it's simple. Okay? Now, let's go back up here. So we know what X bar is. What is the length? What's the length of the connection? 9 inches. Outside bolt to outside bolt. Okay? So L sub CON is 9 inches. And I'll say from, I know I wrote an R, but it doesn't look like it did. From connection diagram. All right. So therefore, U2 1 minus x bar over L, which is 1 minus 0.695 over 9 inches equals what? We'll say 3 decimal places just to make sure we're all getting the same thing.
0.923.
0.923. Second? Now, that's case 2. We also have case 7. Now, how do we deal with case 7? How does case 7 work? Well, let's see. So, let's look here. This is case 7. So, case 7 says W, M, S, or HV shapes, or T's cut from those shapes. That fits. Okay? So, we have 2 branches that go off this. This lower branch talks about the web, right? So, we don't care about that. What about up here? With the flange connected with 3 or more fasteners per line in the direction of loading. So in the direction of loading, we got to have 3 fasteners, right? So here's our tension member. How many fasteners are per line in the direction of loading? 4, right? 1, 2, 3, 4, right? So we definitely have that. So this is our model, right? And our model, what are we doing? We're comparing the flange width and 2/3 of the depth. Remember how I said, trust me, we're going to need those values? Do you trust me? Told you we need them. So we need the flange width and we need 2/3 of the depth, okay? So going back up here, or going here, so the flange width, we already looked that up. Flange width was 6.5 inches. What is 2/3 of the depth? So it's 2/3 of 7.93 inches. I think that's what it was. Yeah. What is that?
I got 5.29. You're right.
Second. So if I were to compare the flange width and 2/3 of the depth, the flange width is bigger, right? And if the flange width is bigger, what do we get for U7? 0.9, right? Because we go here and we say if the flange width is greater than or equal to 2/3 of the depth, U is 0.9. So U is 0.9, so that's U7. So, what's our controlling case? So we have U2 is 0.923, U7 is 0.9. Man, in that diagram, 7 looks like a 2. So, what do we use for U? Which value do we use? U2, because right here, the text here in the diagram says if U is calculated for case 2, the larger value is permitted to be used. So we're going to go with U2. U2 0.923. So now let's go back up to this. Net section fracture. 0.75, FU, net area, and now we know this, right? So by golly gosh gee, let's go ahead and compute this net section fracture capacity finally. So, by the way, hold on, help me out. What did we get for gross section yielding when we did this? What did we get? I think it was 318.6 kips.
Yeah.
Okay, let's just have that up here to reference. So BPN in this limit state is 0.75 FUAN times U, which is 0.75 was 65? Yeah, we're on A992. Net area, what was the net area?
5.68.
5.68. And what's the, well, we're using 0.923. So what do we get for VPN? And let's do that to one decimal place, because at this point it doesn't really matter.
255.6.
255.6 kips. So now we have another limit state value, or capacity. Okay, so we've got gross section yielding, and we've got net section fracture, okay? So the first question I want to ask is, which one? What's the capacity, okay? So let's look at design capacity, how about, no, let's not call it that, let's call it factored resistance. I'll just call it yielding, 318.6 kips, fracture, 255.6 kips. So if these are the only two limit states that we are considering, and I asked you, how much load can this thing hold up? What's the answer? The smaller one, right? Because if I start yanking this, like if I pull it, 0 kips, 1 kips, 2 kips, 3 kips, 4 kips, 5 kips, 6 kips, keep going, I'm going to hit this number first, right? So what this is saying is that it is going to fracture at this load and yield at this load. This is what's going to control the behavior, right? This governs the design, right? So we say this governs, there's that word again, and the capacity is 255.6 kips. All right? Okay. Now, how do I know, but what was I asked at the very beginning? Can the member safely withstand these loads, right? What were those loads again? Remind me.
Dead load is 80 kips, and live load is 9 kips.
Okay, so what that means is we now need a factored load. So our first load combination, 1.4 times the dead. Which is what is 1.4 times 80?
112.
112. What about our second? 1.2 times the dead plus 1.6 times the live. Those of you that have had concrete design, this should be pretty familiar, right? You've done these before, I know you have. 1.2 times 80 kips plus 1.6 times 90. And what do we get for this? Say it again?
240.
240. Do I have a second?
Yeah.
240. Now, if you go to, so let me just make a couple points on this. If you go to our LRFD load combinations and you just look at some of these other combinations, so the third one, 1.2 dead plus 1 times the live, that's not going to give you a higher answer than load combo 2. No point in checking it. Same thing with this one, this one, this one, and this one. So really, these two, if all you're given is dead and live, are the ones that you need to check. And if I'm being honest, in most real-life scenarios, really only 2 is the one that you need to check. I bet those of you that have had concrete design, you probably got to a point in the class where you really only use this one. Am I right? And that's how we're going to get to it here. Is that you can really just look at this problem and see that's going to give you the higher answer. So if you go back to these factored loads, so which factored load do I use? I use the one that gives you the higher answer. So PU is 240 kips. So what can you tell me about this tension member looking at these two numbers? It's a safe design, right? Because it can withstand 255.6 kips on it, and I am loading it with 240 kips, right? So is the member good? The member's good. So what was the first question that was asked? Can this member safely resist these loads? Yes. Typically what I will write is member is adequate. Now, we were not asked to do this in this problem, but I'm going to introduce a new term to you real quick. We're not going to use it until we get to design, but I want to look at efficiency. Efficiency is the load over the resistance. Bridge engineers call these performance ratios. So what is 240 over 255.6? 0.94. Give me one more decimal, please.
Or it'd be 939 then.
Okay, 0.939. We're going to talk about that number here in a bit, but how many of you ever watched Price is Right? Okay, you know how I like to spin the wheel? What's the thing you can't do? Can't go over $1? Yeah. Right? So if this number is over 1, that means there's more load than resistance, and that's no good, right? And for tension members, and when we get into design, if your efficiency is 0.9 or better, you're good to go. We'll get to that later. Trust me. Last thing I want to do real quick is do a quick slenderness check. This will be real quick. How long was the member? 40 feet? Which is 480 inches, if my mental math tells me it is right. We need to look at R min. What is R min for this member? Is it RX or RY? RY. And what was RY? 1.61. RY, 1.61 inches. So therefore, what is L over R min? It's 480 over 1.61 inches. What is that?
I got 298.14.
Getting ahead of myself. 298.1.
14. Where are you at?
This good. This will be good for our discussion, which is fine. Second. So what does this mean?
Barely.
Barely, but it meets it, right? So what we'll say is member meets slenderness. Slenderness limits. What do you think? It's not that hard. All this is just putting everything together we've been doing for the past few lectures all in one lecture. I've been teaching this class for a long time, and I found it's usually easier to just handle each one of those little pieces one at a time and then do it. You know. So what we're going to do next time is we're going to do another problem like this, where we do the whole thing, but it's going to be a different shape. It's going to have stagger. There's going to be some new techniques that we got to do about unfolding the angle and whatnot, but we'll get to that next time. And then next week, we get into the wonderful world of design. I'm going to pull the QR code up again, but that's all I got, everybody. I will see you all.